Alright, so in this video, we're going to take a look at how we can determine the Lewis structures for polyatomic ions. We're not going to do anything ultra complicated, we're just going to do a couple examples here just to illustrate that we can use the same steps that we would use when we draw the Lewis structures for anything. There's just a couple things more that we need to consider when we're dealing with our polyatomic ions. Okay, so for example, let's use the nitrate ion, so NO3 with the minus charge, so that's nitrate. And when you practice your Lewis structures, again, with the videos that you would have seen already, I show one way that I use to draw Lewis structures. If you look online and you Google things, you may find other ways, other strategies to draw Lewis structures. It really doesn't matter which strategy you use, as long as you end up with the right structure. So the way that I do it, I find that I have an automatic check and balance as I go through my steps, and I usually, more often than not, end up with the correct answer. So the first thing I need to do here is to determine the number of valence electrons, so the total number of valence electrons I'm working with. Because remember, in your Lewis structures, that's all you're concerned about, right? Is the valence electrons. Those are the ones that are most important. So I look at my formula. I have nitrogen, and I have one of those. Nitrogen's in group 5, so we have 5 valence electrons. We also have oxygen, and we have 3 of them. So oxygen's in group 6, so 6 times 3 is 18. So that's going to give me 23 valence electrons. And what you'll see now, and this is the extra step we need to consider when we're dealing with ions, we need to look at that charge. And in this case, nitrate does have a -1 charge. That means now that we have an extra electron that gives us that negative charge. So what we need to do is we need to account for that in our valence electron count. So we're going to add 1 electron to this. So then when we draw our structure, we should end up with, our structure should contain 24 valence electrons in it. Right? So that's the only other step here that we're introducing that we haven't seen before when it comes to drawing Lewis structures. So we have our count of valence electrons. The next thing we need to do is to draw a basic layout of the atoms. And we've talked about some general strategies and trends that we're going to see. So in this case, if we have NO3, with a minus charge, usually the thing that you have just one of, and we'll stick that in the middle. And if it's in the middle, that means we're going to have our oxygens all the way around. All right, so we have a basic layout. Then we're going to connect everything with a single bond to begin with. So the nitrogen gets connected to each of the oxygens with a single bond. So they're all stuck together now, right? That's the glue that's going to stick all these atoms together. They're covalent bonds. And then, starting on the outside, we're going to give the outer, or the peripheral atoms, in this case they're all oxygens, we're going to give them enough or sufficient electrons to make them happy. And then in these cases, in all 3 cases, that means giving them a total of 8 electrons, right? So right now, this oxygen here on the left side has got 2 leaded sharing, so we give it 6 more, so 2, 4, 6, 8. And you can probably see that that's going to be the case for all of these oxygens all the way around. They all are going to need 3 more lone pairs on them to satisfy the octet rule. So we've made all the peripheral, the outer atoms happy. Then we need to consider the central one, which is the nitrogen. Before we do that, though, we want to make sure that we haven't gone over, or we've already used all the 24 valence electrons. So when we count, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Right? So those are our 24 electrons. We cannot add any more electrons to this structure. We've already reached our limit. we've seen that the oxygens are good. They have their octet. The nitrogen, though, here in the middle, right now, it only has 2, 4, 6, right? So it needs 2 more. And we cannot just stick 2 more electrons as a lone pair on here because we would end up with more than 24. We can't do that. We just established that we can only have 24 electrons. So when your central atom is electron deficient, what we can do is we can start moving electrons to make multiple bonds, double or triple bonds, and we move electrons as pairs, right? So we can take, for example, this lone pair on that oxygen, and we can move it in, and we can make a double bond now between the N and that O. So I'm going to get rid of those 2 electrons because I just moved them. And now my nitrogen is happy now because it's got those 4 electrons that are being shared here in that double bond, plus 2, that's 6, plus another 2, that's 8. And I still have the 8 electrons around this oxygen on this side, right? So we have our 24 valence electrons in our Lewis structure for NO3 minus. The last thing we need to do is, because this now has a charge on it, we need to indicate that charge in our Lewis structure, and the way that we do that is we put our Lewis structure in big square brackets, and then we put whatever the charge is on the outside, on the top. So that's nitrate, Lewis structure. You are probably thinking to yourself, well, hang on a second, why couldn't I move, if I wanted to, if I felt like it, why couldn't I move that pair of electrons to make a double bond here? Or why couldn't I move that pair of electrons to make a double bond on top? Well, the answer is you can, by all means, move any of those pair of electrons, but you'll end up with the double bond in any of those 3 locations, right? So if I move it from the top, then I have this as my Lewis structure. I moved it from the left side, then I have my double bond on the left, and then I end up with this as my Lewis structure. These are all acceptable for Lewis structures. The truth is the correct Lewis structure is kind of a hybrid between all these 3. But for our intent and purpose in this class, if you drew any of these would be acceptable. All right, so that's if you have a polyatomic ion, and in this case, we have a negative charge, and we're going to add, whatever that charge is, we're going to add that many electrons to our electron count. So what would happen if we had a polyatomic ion with a positive charge? So let's say now we have ammonium ion. You probably remember ammonium from the ionic bonding lab. And ammonium has the formula NH4 with a positive charge. So again, we're going to count our valence electrons. We have 1 nitrogen, nitrogen is in group 5, so that gives us 5. We have 4 hydrogens. So hydrogen has 1 valence electron, times 4 gives us 4, so that's 9 valence electrons. And now you'll see that our ammonium has a positive 1 charge, and we need to account for that in our electron count. So if we have something with a positive charge, that means it's got fewer electrons than protons, right? So we're going to take that many electrons away. So we're going to subtract 1 electron from that. So we take away 1 from 9, and we end up with 8 valence electrons. So when I draw my structure, I need to have those 8 electrons in it, right? So it's the opposite of what we did when we had a polyatomic ion with a negative charge. We added those electrons in. We have a polyatomic ion with a positive charge. We take those many electrons away. So then our layout that we're going to have here for NH4 plus. And then you probably know by now, you've practiced a lot of these, hydrogen never goes in the middle. It's always on the outside, right? Kind of like leaves on a tree. So the nitrogen then has no choice but to go in the middle, and we have our 4 H's on the outside. We're going to connect everything together with a single bond to begin with. Right, remember a single bond, a single line represents 2 electrons. So if I just pause for a second, that's 2, that's 4, that's 6, and that's 8. Those are my 8 electrons. Right, my structure cannot have any more. So right now, if I look and I look at each of these atoms individually, remember hydrogen is an exception to the octet rule. It's one of the very, very important and common exceptions to the octet rule. It only needs 2 electrons to be happy. And it's got those 2 electrons right here. And that's the case with all of these hydrogens. They're all perfectly content with those 2 electrons that they're sharing. So they're good. And then the nitrogen in the middle, well, guess what? It's surrounded by 4 single bonds, and those are 8 electrons. So the nitrogen's also good, right? So the H's are good. Put a little check mark next to them. The nitrogen is good. So everything's good in terms of being stable and giving them enough electrons. The last thing we have to do, this has a charge on it. We're going to put the charge on the outside. All right, so this is just another little wrinkle when it comes to the Lewis structures. In some cases, you won't see them very often, but in a couple cases, you'll see polyatomic ions, and this is how you will address those when it comes to drawing the Lewis structures.